So how do we actually know what a virus looks like? I mean, really looks like. How can we possibly design drugs that fight diseases at a molecular level? Well, the answer comes from this incredible journey, a quest to see a world that's completely invisible to us. This is the story of the electron microscope. And this quote from Nobel laureate Dr. Alan Finkel just hits the nail on the head. It is absolutely not an exaggeration. Think about it. Almost every single major scientific breakthrough, from understanding what bacteria are to creating brand new materials, all of it stands on the shoulders of our ability to see the unbelievably small. But look, this is not just a history lesson. Not at all. Today's most advanced microscopes, they're on the front lines of our biggest battles. They're not just tools for looking at things anymore. They're tools for taking action. So where are they making the biggest difference right now? Well, if you want to create a treatment for something like Alzheimer's or cancer or even a virus like Zika, you first need a detailed 3D map of the enemy. It's like you have to see the exact shape of the proteins and viruses that are causing all the trouble. And modern electron microscopy, it gives scientists that perfect atomic level blueprint. Okay, so to really get how we got here, we have to rewind a bit. We have to go back to this fundamental problem that literally stopped science cold for decades. Scientists knew there was a whole smaller world out there to explore, but they couldn't see it. They had hit a wall made of light itself. So, what was this wall? It's something called the diffraction limit. The easiest way to think about it is like this. You can't use a really thick paintbrush to paint a super tiny dot, right? Well, in the same way, you can't use the wavelength of visible light, which is actually pretty long, relatively speaking, to see things that are smaller than those waves. The light just kind of washes right over them, leaving them totally invisible. And this limit has a hard number, about 200 nanometers. Now, to put that in perspective for you, a single human hair is about 100,000 nanometers wide. So 200 nanometers was the absolute theoretical best you could do. It didn't matter how amazing your lenses were. You simply could not see anything smaller than that using light, period. And this is what was so unbelievably frustrating for scientists back then. They could see a whole bacterium, no problem, but they couldn't see the tiny viruses that infect it. They could see a yeast cell, but not the little protein machines whirring away inside it. The very building blocks of life and of disease were just sitting there, completely hidden in plain sight. So it was clear, to see smaller things, you needed something with a much, much smaller wavelength than light. And the solution? Well, it came from a totally wild, revolutionary idea. What if, instead of using photons of light, we used a beam of electrons? And what's just incredible is how fast this all happened. I mean, look at this timeline. In 1924, this guy, Louis de Broglie, he proposes that electrons, which everyone thought were just particles, also act like waves. And these waves are thousands of times shorter than light. Just 3 years later, it's proven in an experiment. And by 1933, less than a decade after the idea, Ernst Ruska had built a working microscope that smashed right through that old wall of light. The very first version was called the Transmission Electron Microscope, or TEM. So how does this thing work? Well, the idea is actually pretty simple, but it's super powerful. Instead of passing light through a sample, you shoot a beam of electrons right through an incredibly thin slice of it. Then you use magnetic fields like lenses to focus that beam, and that creates this super high-resolution 2D picture of the sample's insides. Being able to see through things was a massive, massive leap forward, but of course, it immediately brought up a new question. What if you didn't want to see inside something? What if you wanted to see the intricate 3D surface of, say, an insect's eye, or the texture of some new metal? Yeah, for that, you'd need a totally different approach. And that need is exactly why we got the Scanning Electron Microscope, or SEM, back in 1956. So instead of passing electrons through the sample, the SEM scans a beam back and forth across the surface. This creates this incredibly detailed, almost 3D-looking image of its topography. So think of it this way. TEM shows you what's on the inside. SEM shows you what the surface looks like. They're two sides of the same coin, two essential tools for answering different questions. But there was still one enormous problem left to solve, especially for biologists. The electron beams you need to get these amazing images are really intense. So intense, in fact, that they would just vaporize the delicate, fragile proteins and molecules of life that scientists wanted to see the most. The very act of looking at something was destroying it. And yeah, that became the central challenge for decades. How in the world could you get a perfect atomic level picture of a biological molecule, in its natural working shape without having the microscope's beam just tear it to shreds? The answer, it turns out, was just beautiful. Don't just freeze it, flash freeze it. This technique is called vitrification, and what it does is cool the sample down so ridiculously fast that ice crystals, the things that would normally destroy the sample, don't even have time to form. Instead, the water just instantly turns into a glass-like solid, locking everything in place, perfectly preserved and ready for the electron beam. This huge breakthrough, which actually led to a Nobel Prize in 2017, was really the work of three key pioneers. You had Jacques Dubochet, who developed the whole vitrification freezing method. Then, Joachim Frank created the genius computer software that could take thousands of kind of fuzzy 2D images and combine them into one sharp 3D model. And finally, Richard Henderson proved that it could all work together to actually see a protein at the atomic level. That whole package deal, that's what we now call cryo-EM. So, when you just take a second and step back, the progress we've made is, well, it's just breathtaking. I mean, in the span of just a few centuries, we went from basically stacking a few pieces of glass in a tube to visualizing the individual atoms that make up our entire world. And that brings us right here, to today. The most powerful electron microscopes can magnify something up to 10 million times. 10 million times. That's a scale that is it's almost impossible to wrap your head around. It allows us to work in a world that, not that long ago, we could only dream about. This journey has literally changed our reality. It's given us the tools to map our most deadly diseases, to build new materials one atom at a time, and it leaves us with this one final, really exciting question. Now that we've conquered the world of the infinitely small, what other invisible worlds are out there just waiting for us to discover them?